Hello, this is Innovative Engineering Solutions with the Affordable Light Project, and we are presenting our work from Phase 2. Throughout this presentation, we'll go over our concept generation and concept selection, how we came up with our primary concept, an overview of the bill of materials and economic analysis, some updates we have made since Phase 1, and an overall summary.
This provides a brief overview of report motivations. This can be found within our problem statement, which is unchanged from the last report, and that would be people without access to electricity, such as rural, undeveloped areas, need a compact and long-lasting source of light that does not depend on periodic replacement of a power source. It is estimated that we will fit into a market with production values between 55,000 and 92,000 units, given a 0.3 to 0.5% market share. These numbers were found with a total market of $1.2 billion, and which would be multiplied by our market share and then divided by the total cost of each unit. Our cost of the unit will also be discussed more later on in the bill of materials.
For our concept generation phase, we created a functional decomposition. The primary function for our concept was light a reading area for an extended period of time. We came up with this function by considering all the customer requirements from the house of quality. We then came up with 4 sub-functions. The first one was transform energy. We need a means of inputting the energy, storing the energy in terms of potential energy, and then transferring it from storage in order to emit light. Our next one was establish placement. We need a means of supporting the device and positioning the device. Next, we wanted our device to be portable, so we need to transport the device, which means grasping the handles and carrying the device. Lastly, we wanted a durable device, so it needs to be able to avoid breakage. So we need to cover the device, add padding and insulation to protect it from drops, and seal the device from water and dust. After creating a functional decomposition, we created a morphological chart with different ways to carry out each subfunction. Using gut feel, we then picked 15 concepts by selecting a solution from each category, as shown by the red circles. In this particular example, we picked spring potential energy as the way to store the energy, a motor to transfer the energy, an LED to emit light, a 3D printed case, electrical switch, and to offer portability and stability, we offered an ergonomic grip and a flat surface.
Our first concept is the plastic spring-powered LED light. This idea uses a spring to store energy, then transfers to a motor which then powers the LED. Our second concept is the stainless steel shake LED light. This is a flashlight that works through induction to power the LED. The plastic gravity potential energy LED light uses gravitational potential energy by using a weight to turn the motor that will power the LED. The product is in a plastic casing and has a stand for support. The portable gravity-powered motor for an LED in a sealed case also uses gravitational potential energy, and it has a hook for portability. To choose between our top 3 concepts, we created a decision matrix. We chose the gravity light as our datum, because from the house of quality, this was our main benchmark. We added values to how much the design met our customer requirements. From this, we decided to go with the spring-powered light as our solution.
The highest weighing concept from the decision matrix was the plastic spring-powered LED light. There have been 2 iterations of the primary concept, V1 and V2. V1 was designed as a modular prototyping base to provide a platform to optimize performance. It was designed to be easily manufactured using the resources available at Purdue University. V2 was iterated to meet and/or exceed all the engineering specifications, as well as being cost-effective to manufacture. V2 meets the engineering specs decided in Progress Report 1. It has a 600 cc volume, a low weight of about 1 pound, and an LED rating of around 20 lux. It runs for a predicted 27 minutes and costs about $20.54 to the customer. As you can see in the CAD renders, the wind-up spring sits on the lower roller. The user will use the handle to wind up the spring onto the upper roller. When the user allows the spring to unwind, it is connected to a generator built-in gearbox through an O-ring driven pulley. We have engineering models that prove that the optimum ratio for the pulley to be 2.8 to 1. The potential energy of the spring is converted into electrical power to power the LED. The LED is facing in a slight downward angle to be optimal for reading. As you can see, comparing engineering benchmarks with other products, we can see that our renewable light is a good competitor. It has a small footprint, low weight, decent lux, runtime, and setup time, and finally, a competitive cost.
Each part was evaluated for cost estimation in our bill of materials. The parts highlighted in light green are the purchase parts, and they include smaller objects like screws, O-rings, and LEDs, which are cheap to purchase or are too complex to be manufactured simply. The parts in gray are the custom manufactured parts, and all will be made using ABS plastic through injection molding. Mold making costs, material costs, and labor costs are all factored into their totals. The two minor assemblies, the gear drive assembly and the case assembly, make up the final design assembly. They consider labor costs at $60 an hour for assembly, which is estimated to be about 5 minutes total if it is automated. And the total cost of one unit is $20.54, which is just above our target of $15. Using the low and high production estimations found through the market research, we performed an economic analysis across 15 quarters. The two graphs show the net present value with interest over this time period. The high production estimation results in a larger net present value overall with the same initial investments into production research and preparations, making it the more profitable venture over time. The differences between the low and high production estimates is shown in this table. As you can see, the break-even point for the low estimate will happen 2 quarters later than the high in the 9th quarter. The rate of return is 97.5 for the low estimate and 163% for the high, and the return on investment is 38% for the low and much higher, 82% for the high. Our product motivations and target consumers remain the same throughout phase 2, but additional research was conducted on the primary consumer group of those in developing areas through the form of interviews. And these 2 interviews changed the importance of the design functions and their weights. And a change of note was the increase in the value of durability. And it now joins cost and brightness as being the 3 most important for this consumer group. While the specific engineering specifications did not change, we're still using the same measures like weight, brightness, and cost, to name a few, but we did change the unit of weight from kilograms to pounds to match our CAD program estimations. And these changes in the customer requirements and specifications only slightly shifted the design performances, but still resulted in the same top 4 designs as was mentioned before. And our problem definition has not changed throughout phase 2.
The main changes from OR1 are that there is no longer a prototype in phase 2 and 3. This also got rid of the technical posters in phase 3. In brief, phase 2 began with the functional decomp and the bill of materials. Using the BOM, we conducted financial analysis. We began the engineering drawings, which is due in phase 3. Then came OR2 and PR2 and the phase 2 design review. In phase 3, we will continue engineering modeling and compile a prototyping report, then present OR3 and PR3 at the final design review.
In summary, we came up with the design of the spring-powered LED light to eliminate the need for batteries using a functional decomposition, a morphological chart, and a decision matrix. The bill of materials estimated that each unit will cost $20.54. And finally, our economic analysis estimated that we will break even around the 7th to 9th quarter with a return on investment of 38.52% up to 82.30%, depending on the number of units produced.